So, are there any questions about the homework? Has anyone looked through that yet and have questions yet? So like I said, I wouldn't wait too long to look at it. At least make sure you understand what the questions are asking. And definitely don't wait until the last minute to start working on it. Yeah?
For 2A, are you looking for a path or a tree?
I believe, I have to refresh my memory on what I asked, but basically I think it's the tree was what I was asking for there.
The problem description talks about identifying a path.
Yeah, I don't recall where did you see the word? Oh, yeah, I guess I used the word path, but really it's supposed to be a full neuron, so it's a tree really rather than a path. Any other questions? Okay, so today I'm going to be talking about some material that is kind of a bit off the main topic of the class. There's really essential background, and I know some of you have probably seen this before, but I think it's still useful to have a refresher. Some of you probably haven't. But basically the issue here is that I'm going to be covering some basic concepts and terminology from the field of linear algebra. So it's one of the limitations of a very broad sort of class like this, that it assumes material from a lot of different directions, and there are only so many prerequisites we can assume. So I teach the class assuming you haven't had linear algebra. I know some of you have, but this will at least make sure everyone's on the same page. Obviously, one lecture is not a substitute for a linear algebra class. If you're going further in computational or modeling work, I would recommend you take a real linear algebra class if you haven't, but this should get us through what we need for this class. Just by a show of hands, how many of you have taken linear algebra or something equivalent? Okay, so maybe half. Okay, so hopefully this will be useful to all of you. All right, so this is a topic that I kind of need to cover because it comes up in a lot of different contexts and things we'll be looking at going forward. The immediate need for it comes up in considering algorithms for continuous optimization. So there's actually quite a lot of linear algebra that comes up in both our next topic, which is general or unconstrained optimization, and then constrained optimization, which we'll be seeing later. So we kind of need it then. And when we get into simulation, it will come up in context of Markov models, which are the main way that we are going to be looking at discrete simulation, and differential equation models, which are the main way that we'll be looking at continuous simulation. So linear algebra is very central to how we analyze both kinds of models. So we don't need to know it in great depth, but we do need to know at least some basic concepts and terminology, and I'll also be presenting some linear algebra algorithms in the next lecture that we'll need to know at least a bit about. But roughly speaking, linear algebra I think is not that complicated. It's basically the study of matrices. So matrices in the general case can be thought of as a set of two-dimensional arrays. So matrix we would commonly write in brackets like this. It would have some number of rows, which we'll call m, so m rows running from top to bottom, and then some number n of columns. Basically, columns run top to bottom, rows run left to right. And then it would have a set of elements running, for example, A11 through A1n, A11 through AM1, and through AMN, or in general, we would have an element Aij and some arbitrary row I in column j. So that would be more or less how we would write a matrix, and we would refer to this commonly as an m by n matrix. Okay, so is everyone with me so far? All right, so one important special case of a matrix we'll commonly see is a vector. So a vector is a matrix where one of the dimensions is 1, so either m is 1 or n is 1. And we'll typically write this either in the form where we have an m by 1 matrix, or m by 1 vector running v1 through vm. And this would be commonly referred to as a column vector. Or we could have a 1 by n vector, so that would be elements v1 through vn, and this we would refer to as a row vector. There's one other special case we need to care about, and that is a 1 by 1 matrix. Does anyone know what that's called? Yes, that would be a scalar, and a scalar would just be a single number s. So canonically, we'll have some notation we would often use to try to disambiguate these things when it isn't clear from the context. So a matrix will commonly denote with a capital letter, so capital A, for example, would be this matrix. A vector we'll commonly write as a lowercase letter with an arrow over it, so these would be vector V, and a scalar, just a lowercase letter with no decoration to it. Sometimes I will forget to put the arrows on or something like that. I'll try to put them on when it's at least necessary to disambiguate things. So is this clear so far to everyone? Okay, so one special case of matrix we often need to worry about, that will come up quite a bit, is an n by n matrix. So the two dimensions are the same, which is also known as a square matrix. And there's some terminology we need to know about when referring to square matrices. So in a square matrix, we'll commonly use some notation to describe different pieces of the matrix. And one particularly important piece is going to be the elements of the form D11, D22, D33, etc. So basically elements running from the upper left to the bottom right, which we will know of as the diagonal elements of the matrix. These are diagonal elements. And we refer to elements above the diagonal, so that would be elements, let's say U12 through U1n through Un-1n as upper triangular elements. And similarly, we would refer to elements below the diagonal, so that would be L21 through Ln1 through Ln-n-1, etc., as lower triangular elements. We'll also sometimes refer to some special cases of matrices in which some subsets of these elements are zero. So if you have a matrix that consists of all zero entries except for the diagonal, so the diagonal is potentially non-zero entries, everything above and below it is zero, then we say that this is a diagonal matrix. And we can similarly refer to an upper triangular matrix. So an upper triangular matrix would have potentially non-zero diagonal elements, as well as potentially non-zero upper triangular elements, but all the lower triangular is zero. That's an upper triangular matrix. And in contrast, we would also have lower triangular matrices. So in a lower triangular matrix, again, the diagonal elements may or may not be zero, but you would have at least some non-zero elements below the diagonal, but all zero elements above the diagonal. So that would be a lower triangular matrix. So these will just be some terms that we'll be encountering later, so you should be aware of what it means when I refer to a diagonal matrix or upper triangular or lower triangular. So any questions about any of that yet? Okay, so we will often want to do arithmetic on our matrices. So we need to know something about matrix arithmetic and matrix operations in general. So I want to go through a few of the basic kinds of things we can do to compute with matrices. Okay, so one of the simple things we might want to do with two matrices is add the matrices. And we can refer to the operation of addition on matrices. So if we have a matrix A and a matrix B, we can refer to the sum of those A plus B. And that will work in the following case. So let's say we have an m by n matrix A, runs from A11 through A1n, AM1 through AMN. That can only be added to a matrix with the same dimensions B. So B also has to be m by n, so that runs from B11 to B1n, Bm1 to Bmn. And the sum of those two matrices is simply the matrix you get by pairwise adding the individual elements in the matrices. So in other words, the upper left corner, position 1, 1 of the sum matrix would be A11 plus B11. The next element next to that would be A12 plus B12, A13 plus B13, etc., out through A1n plus B1n. And likewise in the next row, A21 plus B21, A22 plus B22, etc., until we get down to AMN plus BMN. So, any questions about this? All right, so subtraction is basically the same thing. If we want to take A minus B, we just pairwise subtract the individual elements. So in A minus B, we would have the upper left element would be A11 minus B11. Next one would be A12 minus B12, etc. up through A1n minus B1n, and so forth, down to AMN minus BMN in the lower right corner. Okay, so we take a simple example here. Let's imagine we've got the matrix A that looks like the following: 3, 0, 4, 9, 1, 2. And matrix B, we will say, is 4, 1, 6, 2, 0, 3. Then if we want to find the matrix A plus B, we would start adding the elements pairwise. We get 7, so 3 plus 4, 0 plus 1, 6 plus 4. And what would we have in the lower row? Yeah, so 11, 1, 5. Okay, and A minus B would be computed basically the same way. So 3 minus 4 would be minus 1, minus 1, yeah, minus 2, 7. Okay, so that's addition and subtraction of matrices, and that's pretty straightforward, I think. All right, so things start getting more complicated from there. So before I can get to introducing other arithmetic operators, there's one kind of special matrix operator I need to mention that we'll use as some of our terminology in describing these. And that's something called a transpose operator. So a transpose of a matrix is something we'll commonly write as a superscript T, so A to the T means A transpose, and all the transpose means is flip the rows and columns of the matrix. So if we have a matrix, let's say 1, 2, 3, 4, 5, 6, and we take the transpose of that, then what we would do is change this M by N matrix into an N by M matrix. In this case, it would be the matrix 1, 3, 5. So column 1 becomes row 1, and 2, 4, 6. So column 2 in here becomes row 2 in here. So is that clear to everyone? Okay. So that will come up shortly in starting to describe matrix multiplication. So matrix multiplication is a little more complicated than matrix addition and subtraction. I think it helps to start by talking about the special case of vector-vector multiplication. So vector-vector multiplication just means matrix multiplication, where we assume we're multiplying two matrices that are vectors, and they have dimension 1 in one of their two dimensions. And there are kind of two versions of this that are special cases of the general matrix multiplication, and then there's another kind of vector multiplication that I'll just mention that really doesn't fit into the same model. But probably the most common sort of vector multiplication you'll see is what's referred to as a dot product, also known as an inner product. So let's suppose that we have two vectors, and I'll call these vectors u, and u will be a column vector, so it'll run u1 through un, and I'll assume we've got a vector v, which for the present purposes we'll just assume has the same length. So it runs v1 through vn, also a column vector. Then the dot product, sometimes written u dot v, or you'll also sometimes see u transpose v. This would be equivalent notations. The dot product is what we get by basically taking the sum of the pairwise products of the elements of those two vectors. So in other words, if we have the dot product, or u transpose v, for these vectors u and v, this would be simply the sum I equals 1 to n of ui vi. So if we take an example, let's say u is 1, 2, 3, and v is 1 minus 1, 2, then to compute u dot v, what we would do is take first element of u times the first element of v, that's 1 times 1, plus the second element of u times the second element of v, 2 times minus 1, plus the third element of u times the third element of v, 3 times 2, and if we add that up, we'll get 5. So the dot product is going to be a scalar. It will always convert two vectors of the same length into a scalar. Okay, any questions about that? All right, so the dot product is going to come up fairly often in operations we'll be doing later on, and also will help us in a few minutes when we get to explaining the general matrix multiplication. It's also kind of handy when you get into models that involve working with geometry. So it's useful in part because of an identity that if we have two vectors u and v, then the length of the dot product is equal to the length of u times the length of v. I'll explain what this length operator means in a few minutes, times the cosine of theta, where theta is the angle between the vectors formed by these. So if this is u, this is v, the angle between them is theta. It's just a handy thing to remember. And this has, in part, the consequence that if the vectors happen to be at right angles to each other, cosine theta is 0, so the dot product is 0. So it gives you an easy way to test if two vectors are orthogonal. Any questions about that? Okay. So the other kind of sort of standard vector-vector multiplication is something you don't see quite as often, but still good to know about for completeness. And this is commonly referred to as an outer product. And if our vectors are represented as they are here in column format, then this would be written as u v transpose. And u v transpose we could write as, in this case, let's say we've got u running through from u1 to um. So here I'm not going to assume it has the same dimension as v. V will keep as v1 through vn. In this case, it doesn't matter if their lengths are the same. Then the outer product is going to be a matrix of dimension m by n. So this is m by 1, this is 1 by n. The result is going to be m by n. And in particular, it's going to be the matrix of simply pairwise products of elements of u and elements of v. So element 1, 1 is going to be u1 times v1. Element 2, 1 is going to be u2 times v1. 3 times v1, etc., up through times v1, and likewise u1 v3, and so forth out to u1 vn, and likewise down to vn. So that is going to be then the outer product. So the inner product of two vectors requires that the vectors have the same length, and it's always scalar, always 1 by 1. The outer product, that can have any lengths m and n, and the result is a matrix of dimension m by n. Is that clear to everyone? Okay, so there's one other thing you'll often see referred to as a matrix multiplication operator, or excuse me, a vector multiplication operator. And I'll just mention that here, even though it's not so relevant to us, and that is called a cross product. So cross product is something you usually will only deal with in 3 dimensions, and the cross product is defined as follows. So if we've got a 3-dimensional vector u, with elements u1, u2, u3, and vector v, v1, v2, v3, then we would say that u cross v is defined as the following thing: u2 v3 minus v2 u3, u3 v1 minus v3 u1, and u1 v2 minus v1 u2. So it takes 2 3-dimensional vectors, and the output is also a 3-dimensional vector. So this is something that we'll also sometimes see as a way of multiplying vectors, but as I say, it's not so relevant for our discussion today. I just mention it for completeness. It is also useful in part because there's a similar identity to this one here. So this is a vector, but we can still refer to the length of the vector, u cross v. That's equal to the length of u times the length of v times the sine of the angle between them. So the cross product then would have the property that if the vectors are orthogonal to one another, in a sense you have maximum length between them, and the cross product of 2 parallel vectors don't have a length of 0. Is there any questions about this? Okay, so all of that is kind of leading us up to the main reason I wanted to mention these, which is matrix multiplication in the general case. Okay, so, yeah, is there a question?
If we have a vector of a higher dimension, then how does the cross product change according to that?
Well, I'm not sure you would use it in a higher dimension. So it's, and I've never worked with it in higher than 3 dimensions. So I don't know if there is a standard generalization for that. Yeah, and there's some math behind it. You could generalize, but I don't want to say what it would generalize to, because there are different ways you could do it. Any other questions? Okay, so in the general matrix multiplication case, what we would have is the following. So we would have 2 matrices. I'll assume that one of these matrices has dimension m by x, and the other one has to have dimension x by n for some n. So this dimension of the first matrix has to match this dimension of the second matrix, or else this operation isn't defined. Let's just call this matrix A and this matrix B. So A then is an m by x matrix, B is an x by n matrix. The product of them then is going to be a matrix that is m by n, and we can just call this matrix C. That's going to have the following particular property, that any element of this matrix, so C I sub j, which is going to mean the element in row I, column j, Cij is going to be equal to the sum k equals 1 to x of aik b kj. And this is something that we can kind of think of conceptually fairly easily in terms of the operators we've just seen. It's the equivalent to what you would get if you take the ith row of matrix A and the jth column of matrix B and take the dot product of those. So if we refer to the ith row of matrix A as the vector A sub I, and the jth column of matrix B as the vector P sub j, then the dot product of those is going to be Cij. Does that make sense to everyone? Okay, so let's take an example, and that should make things a bit easier to see. So let's say we've got our matrix A as the matrix with elements 1, 2, minus 1, 3, 0, minus 2, and matrix B we will say is then 1, 4, 2, 3, minus 1, 0. And we're trying to find then matrix C, which would be the product of those. So to start with, what would the dimensions of matrix C be? Yeah, it would be a 3 by 3 matrix. So let's take the first element, so element 1, 1, or element C1, 1. How would we compute that? Yeah, so what we would want to do is take row 1 of matrix A, column 1 of matrix B, and take the dot product of those. So that's going to be 1 times 1 plus 2 times 3, which is going to give us 7. If we want to know the next element down, that would come from taking the second row of A times the first column of B. So row 2 of A times column 1 of B gives us element 2, 1 here. So that's going to be minus 1 times 1 plus 3 times 3, which will be 8. And the third element in column 1 of matrix C is going to be 0 times 1 plus minus 2 times 3, which is minus 6. Is everyone with me so far? Okay, and we can follow the same reasoning for the remaining elements. So to get the middle column, we would be taking dot products of rows of A with the middle column of B, and that's going to come out to 1 times 4 plus 2 times minus 1, which is 2, minus 1 times 4 plus 3 times minus 1, which is minus 7, and 0 times 4 plus minus 2 times minus 1, which is 2, and likewise for the third column, that would be dot products of rows of A with column 3 of B. So 1 times 2 plus 2 times 0 is 2, minus 1 times 2 plus 3 times 0 is minus 2, and 0 times 2 plus minus 2 times 0 is 0. So that is the product of these two matrices. So, any questions about this? Okay, so one thing that I think makes it a bit easier to remember this, and in particular to remember some of the vector-vector multiplication operations we talked about before, is to remember that the outer product and the inner product are just special cases of the general matrix multiplication problem. So if we have an outer product, so in this case we are taking an m by 1 vector multiplied by a 1 by n vector, then if you follow the general rules of matrix multiplication that we've seen, what should the dimensions of the product be? Yeah, it should be m by n, and to find each element of that, so let's say element ij of this, we would take row I of this vector, which is just going to be a single element, so it's a scalar, times column I of this one, or column j of this one, which is also a scalar. So the entry we would end up with here is just ai times bj. So that is how we had defined this previously. Likewise, with the dot product. We have a 1 by x vector times an x by 1 vector. So what should the dimensions of that be? Well, in this case, we have 1 by x times by x by 1. So in the general case, what we have to have is an m by x matrix times an x by n matrix gives us an m by n matrix. So here m is 1 and n is 1. So what we end up with is 1 by 1, or just a scalar. And as we saw in the definitions here, the particular value of that scalar should be the dot product of this row with this column. So in other words, just what we call the dot product. So that's just saying that a dot product is a special case of the normal matrix multiplication. Is that clear to everyone? Okay, so it's worth mentioning just one more kind of intermediate special case we'll see quite a bit. This also follows from the normal rules of matrix multiplication. That's just good to be aware that you'll see it quite a lot. And that is multiplication of a matrix times a vector. So if we have matrix vector multiplication, we would have an m by n matrix, let's call that capital M, and we will multiply that by a vector, let's call that V. And what do the dimensions of the vector have to be? It has to be n by 1, so this dimension has to agree with this dimension. And what we're going to come up with then is, well, what would the output look like? Yeah, so the output is going to be an m by 1 vector, and let's call that u. And we can get that vector just by applying the normal rules of matrix arithmetic. So each element ui is going to be the thing we would get by taking the dot product of row I of matrix M with all of vector v. So ui, in other words, is going to be sum k equals 1 to n of mik bk1. So just a single dot product for each element of this. So any questions about any of that? Okay, we can again take a simple example here. Let's say we've got M is the matrix 1, 2, 3, 4, 5, 6. We're multiplying it by a vector V, which we'll say is 1 minus 1, 2. We are going to end up with then a 2 by 1 vector, and we'll get that by taking the dot product of 1, 2, 3 with 1 minus 1, 2. That's going to give us 5, followed by the dot product of 4, 5, 6 with 1 minus 1, 2. That will come out to be 11. So any questions about this? Okay, so before we go further with matrix arithmetic, it's worth pointing out a few properties of these matrix operators we've seen so far. So just good things to keep in mind when you're working with matrix arithmetic. So one of the properties that we'll encounter in which matrices are very much like scalar numbers in our arithmetic is that matrix arithmetic is what's called associative. And associative basically means that if you have a set of matrices and you're multiplying more than two matrices together, so let's say we're multiplying A, B, and C, then it sort of doesn't matter what order we do it in. If we're doing this in exact arithmetic at least, then you'll get the same answer whether you multiply B by C and then multiply A by that, as you would get multiplying A by B and then multiplying the product by C. Now I put those caveats on it because in practice it actually can matter for a couple of reasons. So one reason is that if you're working with a computer, you never have exact precision arithmetic, and in some cases, it can matter in terms of underflows and overflows. Basically, you can get imprecision, and some ways of multiplying might lead to more precision than others. And it can matter quite a lot in terms of computational efficiency if you're working with big matrices. So depending on which order you multiply things in, the runtime may be very different. So basically, each matrix multiplication is kind of an n-squared operation. If you multiply things in ways that shrink your matrices quickly, you can get a faster runtime than if you multiply things more slowly, or if you multiply things in ways that tend to keep large matrices around. Any questions about any of that? All right, so the next property that is much like standard arithmetic is that matrix arithmetic is distributive, and distributive means that if we combine multiplication with addition, so A times B plus C, that is the same as AB plus AC. But one important thing to remember about matrices is that they are not commutative. So commutative would mean that that we can reverse the order in which we multiply things. So a commutative arithmetic would say that A times B is equal to B times A. That is not true with matrices. So A times B can be a different thing than B times A. We can see that with a relatively simple example. Let's say we have the matrix 1, 1, 0, 1 times the matrix 0, 1, 1, 0. If we do the multiplication through, then what we're going to get is that this is, well, it's going to give us 1, 1 times 0, 1, which is 1, 0, 1, 0, 1, which is going to be 1, 1, 1, excuse me, 1, 1 times 1, 0, which is 1, and 0, 1 times 1, 0, which is 0. So that's going to be what we would get doing this multiplication. But if we flip the order of this and say 0, 1, 1, 0 times 1, 1, 0, 1, then what we're going to end up with is 0, 1 times 1, 0, which is going to be 0, 1, 0 times 1, 0, which is going to be 1, 0, 1 times 1, 1 is 1, 1, 0 times 1, 1 is 1. And these, of course, are not equal. Everyone follow that? Okay, so just something to be aware of, that matrix multiplication is not commutative. One other simple property that's worth being aware of is a property of the transpose operator I mentioned previously. This is just a handy thing to remember when you're working with transposes, and that is that AB, so A times B transpose is equal to B transpose times A transpose. So just a simple identity to remember, but it comes in handy pretty often. Okay, so one other concept I wanted to mention with respect to matrices is what's called an identity matrix. An identity matrix is a special matrix we'll sometimes deal with. We would commonly denote this by a capital I. An identity matrix is a square matrix that has ones everywhere on the diagonal and zeros everywhere else. And the identity matrix has the nice property that for any square matrix A of the same dimension, A times I is equal to I times A, which is equal to A. So multiply a matrix by the identity on either side, you get back the same matrix you started with. Right, so any questions about any of that? Okay, so moving on then, I've left out so far one important arithmetic operator, and that is division. And part of the reason I left this out is because there isn't actually a division operator for matrices, but there's something that's almost as good, and that is an inversion operator. So if you have a matrix A, we would denote the inverse of A as A inverse, and is equal to the identity matrix, which is also equal to A inverse times A. All right, so you can sort of think of the inverse as giving you something kind of equivalent to division. So we can't say matrix A divided by matrix B, but we can say that's sort of like A times B inverse, or it's sort of like B inverse times A, and it's problematic that these may be different things, but at least gives you something that we'll sometimes use analogously in the matrix case to division in the scalar case. But there are a few complications we need to know about with matrix inversion. So one of the simple ones is that not every matrix is invertible. So in the scalar case, there's just one number that isn't invertible. Does anyone know what that is?
0.
Yeah, you can't invert 0. So in matrices, there's an infinite class of matrices that are not invertible, and we refer to these as singular matrices. So an example of a singular matrix would be the following. So let's say we've got the matrix 1, 2, minus 1, minus 2. That is a singular matrix, and this has no inverse. An example of a non-singular matrix, the one that has an inverse, would be 1, 2, minus 1, 2. All right, so in this case, we can verify that this matrix is in fact invertible by providing the inverse, and I'll tell you in a little while how you can find these, but in this case, 2/4 minus 2/4, I'm writing it that way for a reason, 1/4, 1/4 is going to be the inverse of B, and we can verify that if we want to. So 1 times 2/4 plus 2 times 2/4 is 2/4 plus 2/4, or 1. So the product of that would be 1. 1 times minus 2/4 plus 2 times 2/4 is 0. Minus 1 times 2/4 plus 2 times 1/4 is 0. And minus 1 times minus 2/4 plus 2/4 times 1/4 is 1. So we can verify that multiplying these together gives you the identity matrix, which tells you that this is the inverse. Now, figuring out that a matrix does not have an inverse is usually not too hard to do. I'll show you a bit later an operator you can use to test very quickly whether a matrix has an inverse. But roughly speaking, the definition of a matrix that is singular, or the thing you would use to test that, is what's called the linear independence of the rows and columns. And linear independence simply means that there is no way to take the rows and columns and take the linear function of them and get back a 0 vector. So in other words, if we were to take the rows and columns, or rows or columns of A, so in A, if we take the columns, we've got a vector 1, 2 is one of the columns, the vector minus 1, minus 2 is another column. So we can say that 1 times 1, 2 plus 1 times minus 1, minus 2 is equal to 0, 0. And because there's a way of combining a scalar times this plus a scalar times this to get a 0 vector, that tells us the columns of A are linearly dependent, and that means that A is a singular matrix. We could do the same thing with the rows of A. So in this case, the rows would be 1 minus 1 and 2 minus 2. And in this case, we could say that minus 2 times this plus 1 times this would give us 0, 0. So that would be another independent test that A is singular. In the case of B, it's not going to be possible to do that, so there's no way of combining them. So in the case of B, we would have a non-singular matrix, and we would be guaranteed that it would have an inverse. Any questions about that? All right, so this question of linear dependence or independence feeds into an important measure of a matrix that we're going to need to pay quite a lot of attention to in the coming lectures, and that's something known as the rank of the matrix. And the rank of the matrix is simply the maximum number of linearly independent rows or columns you can find in the matrix. So in this case, for B, the columns, let's say, are linearly independent. So B has 2 linearly independent columns, which means it has rank 2. For A, we can only pick one of these. We pick a second one. We get a set that is linearly dependent. So we can get at most one column of A in a linearly independent set, which is a way of saying that A has rank 1. And so rank is something we'll often care about when we talk about various kinds of modeling problems, and we'll sometimes see the term full rank. And full rank means that an n by n matrix has rank n. So if an n by n matrix has rank n, we say that that is a full rank matrix. All right, so any questions about this? Okay, so there is a bit more I wanted to say about some special operators on matrices before we move on. And one of these is something that I've actually mentioned briefly but didn't define before, and that is a way of describing the length of a vector, sometimes known as a norm. Right, so norms exist for vectors and for general matrices. I'm going to start by defining them for general matrices. And the notation I used previously was this double bar, so double bar around V. And this is known as the Euclidean or 2 norm. And it's defined as the square root of the sum I equals 1 to n of element bi squared. So the sum of the squares of the elements. It's our standard definition of length of a vector, and that's the most common thing we'll see referred to as the norm or length of the vector. Any questions about that? This is a special case of a more general notation known as a p-norm. And in a p-norm, we would commonly write that as D with the double bars around it with a subscript p. That would mean a p-norm. And a p-norm is defined as the pth root of sum I equals 1 to n of absolute value vi to the p. So the 2 norm is just the p norm for p equals 2, but we could define this for any other kind of norm we want to. So if you want a 3 norm or 4 norm, I guess you could define a 1.5 norm if you wanted to. I've never seen that. But basically, you can define whatever one you want. 2 norm is the most common one, but there are a couple of others we'll sometimes see. Beyond the 2 norm, the most common one you'll see is the 1 norm. So in plain English, what would the 1 norm do? Yes, the 1 norm is simply the sum of the absolute values. So p sub 1 is the sum I equals 1 to n of vi. This has some important applications in machine learning and therefore in model inference context, so it's a good one to recognize. You'll also more rarely see the infinity norm. So can anyone figure out in plain English what would an infinity norm be? You kind of need to take some limits to figure out what this would be. But basically the infinity norm is the absolute, it's the absolute value of the element with largest absolute value. The assumption would be that when you raise everything to the infinity power, the largest one overwhelms all the others, and then when you take the infinity root, you just get that back. So that's how we define an infinity norm. So sometimes you'll see that used. There is also a concept of a matrix norm. There are different ways to define that, but the most common way you'll see is that a matrix P norm, let's say A sub P, would be defined as the maximum over all vectors X of A times X, P norm divided by P norm of X. So this is something that's a little trickier to compute, but it comes up in some contexts when people worry about analyzing efficiency of some of the algorithms we'll see later. So many of them actually depend on the norms of the matrix that you're considering. So just be aware of that concept. But basically, you can kind of think of it as the largest amount by which this matrix stretches a vector when it's applied as a multiple of that vector. Okay, any questions about that? Okay, so one other operator I wanted to introduce that becomes quite important in some of the things we'll be looking at is something that's really special to matrices but has some useful applications for us. And that is an operator known as a determinant. The determinant is a little tricky to explain, but I'll give you a definition for how you can compute it. So we'll commonly write a determinant like an absolute value, so single bars around the matrix, or we'll sometimes write that as just det of A. And to explain a determinant, I need to explain a concept of a submatrix. So if we've got a matrix A, and let's just say that, well, A is maybe m by n, then we can define a submatrix of A. Let's call it A sub ij. And this submatrix is defined as what we get if we pull out row I and column j of A. So in other words, if this is row I and this is column j, just remove those from A, and then you'll get a matrix that is m by 1 by n by, or excuse me, m by 1 by n, or m minus 1 by n minus 1. So Aij is m minus 1 by n minus 1. Just pull out one row or column, and that's what you get. So, for example, if we had the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, then we can define the submatrix A11. What would the dimensions of that be? Yes, this would be 2 by 2, and what would the elements be? 5, 6, 8, 9. And we could similarly define A22, that would also be 2 by 2, that would have elements 1, 3, 7, 9, and so forth. Right, so is this definition clear to everyone? Okay, so we need that definition because the determinant is most easily defined recursively in terms of submatrices. And in particular, the way we would compute this is as follows. Given a matrix A, we would say that the determinant of A, we would compute by taking the matrix A, let's say this is A, and taking, let's say, one row. It actually doesn't matter which row, or it could be a column. But let's just say take the first row of A, and we're going to read across that row, and for each element of that row, we're going to take the submatrix defined by that element's row and its column. So in other words, we'll take element 1, 1, and then we're going to multiply that by the determinant of the submatrix A11. We then subtract from that A12 and multiply that by the determinant of the submatrix A12, add A13, multiplied by the determinant of the submatrix A13, and so forth. Just running through one row or one column of the matrix. And what we get at the end is going to be the determinant of A. Now for a recursive definition to work, we need a base case, and there is a simple base case here. So the determinant of a scalar, so just a single element, A11 is the value of that scalar. And that then gives us a definition we can use for computing determinants. So, for example, if we were working with, let's say, this matrix here, 5, 6, 8, 9, then we could say that the determinant of this is going to be 5 times the determinant of the submatrix, removing the row and column of 5. So that's just going to be the matrix 9, minus 6 times the determinant that we get from removing the submatrix containing, removing the row and column of 6, which is going to be simply the matrix 8. And if we do the math here, that's going to be 5 times 9 minus 6 times 8, or 45 minus 48, or minus 3. So any questions about that? Okay, so there are a few useful things you can do with determinants. So one of the useful reasons for having determinants is that there's an identity that the determinant of A is equal to 0 if and only if, and for anyone who hasn't seen it before, this notation IFF means if and only if A is singular. So the determinant gives you an easy test for whether a matrix is singular. If the determinant is 0, it's singular. If the determinant is not 0, it's non-singular. Determinants are also useful for computing inverses of matrices, but just in the 2 by 2 case. It gets more complicated beyond that. But in the 2 by 2 case, we have an identity that if we have a matrix A, B, C, D, and we want to compute the inverse of it, that's defined by the matrix DA, so flip the diagonal elements, invert the other elements, minus B, minus C, and then divide all of this by the determinant of the matrix, so determinant of A, B, C, D. And the result of that will be the inverse. So again, this only works in the 2 by 2 case, but that's useful enough that it's worth knowing about. And so if we work through the math in this case, the determinant of A, B, C, D, we already worked out here. It's AD minus BC, so we can say that this is going to be D over AD minus BC minus B over AD minus BC minus C over AD minus BC and A over AD minus BC. So that is the inverse of a 2 by 2 matrix. And obviously you can't compute this if the determinant is 0, and you're dividing all the elements by 0. Okay, any questions about that? Okay, so next thing I wanted to mention that comes up here quite a bit when we're working with matrices is the concept of a linear system. So this is a lot of why we care about matrices. They give us a way of reasoning about linear systems. And a linear system is something we've seen before. I showed some examples of this when we talked briefly about linear programming transformations. But typically when we refer to a linear system, in this context, we're talking about a system of linear equalities. So something like 2x1 plus x2 equals 6, 3x1 plus, let's say, 0x2 equals 4. This would be an example of a linear system of equations. And linear algebra notation will often give us a convenient way of writing these systems, but also convenient tools for working with them and solving them. So we could rewrite this particular system of equations and in terms of matrix notation as 2, 1, 3, 0 times the vector x1, x2 equals the vector 6, 4. just a way of rewriting that, but a convenient way of representing these. And very often when we're working with linear systems, we'll get something that looks qualitatively similar to this. So we'll have a known matrix A, we'll have an unknown vector X, and we'll have a known vector B, and we'll often write these as A. So we can see a simple example of how this might work in a biological context. So let's say we were trying to figure out parameters of a contact energy function, like we've seen with protein models before. So let's say we are looking at a simple version of a protein structure where we're using what's called an HP model. So an HP model is a very simple version of a protein amino acid alphabet where we simply say we have hydrophobic residues and we have polar residues. We call those H and P. And we can imagine that we're trying to create a model in which we say that there is some energy that we get to a protein fold from H's bound next to H's. There's some energy from P's packing against P's. Each of those should contribute to some degree to the stability of a protein. And maybe we want to figure out what those are. So we might say that we'll call this a variable x1, we'll call that a variable x2. Those would be our unknowns. And then we might look at some examples of proteins where we might suppose that we've been able to measure the energies of those proteins. So maybe we've got one protein structure in a lattice protein model that looks like the following. So we've got a backbone following this S pattern here, and then we've got two contacts. This particular fold brings this H close to this H, and brings this P close to this P. And let's say we've measured that the free energy of folding this protein is -4 in whatever units we have. Then how could we express what we observe here as a constraint on the values of x1 and x2? Well, we've got one instance of an HH interaction. We've got one instance of a PP interaction. So if x1 is the amount of energy contributed by an HH interaction, and x2 is the amount contributed by a PP interaction, that would tell us that x1 plus x2 is equal to -4. So that would be a linear equality constraint imposed by this structure. And maybe we've got another structure that looks like the following. H, H, P, P, H, H. And this structure happens to bring two pairs of hydrophobics into contact. And maybe this has an energy of -6. Then we would say that this imposes the constraint 2x1 plus 0x2. We have no PP contacts. You'd usually ignore the ones that are in the backbone of the protein, and that is -6. So our system of equations, or a linear system, would be x1 plus x2 equals -4, 2x1 plus 0x2 is equal to -6. Or in linear algebra notation, we would say that that is equivalent to saying the matrix 1, 1, 2, 0 times x1, x2 is equal to the vector -4, -6. And this is what we would mean by a linear system, where we would assume that we're trying to figure out what x1 and x2 are. So does that make sense to everyone? Okay, so in this case, we could probably figure it out pretty easily just by some basic logic and arithmetic, that if 2x1 is equal to -6, then x1 must be -3, and then if -3 plus x2 is -4, x2 must be -1. Everyone follow that? All right, so in the next class, we'll look at more general methods where you can take arbitrarily complicated matrices and solve these kinds of systems. But for now, just be aware that's what I mean by a linear system. All right, so any questions up to this point? Okay, so when we talk about linear systems, we're going to assume that we've got some matrix A, which we'll say is canonically m by n. And this is where we care quite a bit about the rank of the matrix that we're talking about. So if we have a matrix A where the rank of A is less than n, so m would be the number of equations, so that's the number of rows, n is the number of columns, which are typically the number of variables, then we would say if the rank is less than the number of variables, then this is an example of what's called an underdetermined system. So that means you don't have enough equations to pin down the values of all of the variables, and when you have an underdetermined system, normally you're going to get an infinite number of solutions. It's possible to come up with cases where you actually have no solutions, but normally underdetermined means infinite solutions. When the rank is less than m, so that is, we have normally this would come up in the case where we have more equations than we have variables, or so we have more things constraining the variables than there are variables. We end up with what's called an overdetermined system. And in an overdetermined system, usually there are going to be no solutions. Now that doesn't mean that you can't work with either of these. And in the next class and some subsequent ones, we'll see some options for what to do if we're working with a system that is underdetermined or overdetermined. You tend to use different methods in those cases. And the final case, of course, is that the rank of A is equal to n, which is equal to m. This can only happen if they are in fact equal. And then you end up with a full rank system. And in a full rank system, we have exactly one solution. And the main topic of Thursday's lecture will be talking about this situation. So how do we find that one solution when there is exactly one solution? All right, any questions about that? Okay, so we'll revisit this terminology, but these terms will come up quite a lot over the next few lectures in thinking about underdetermined and overdetermined and full rank systems. So just be aware of what these terms mean when I refer to them later. All right, so another concept that is pretty important and that will come up quite a lot when we analyze systems like this is the concept of an eigenvalue and an eigenvector. So if we have a matrix A, and we can find a vector x such that A times x is equal to a scalar lambda times x, then we say that x is an eigenvector of A, and lambda is the eigenvalue of A associated with x. So eigenvalues and eigenvectors will come up quite a lot later on. They'll come up in some of the algorithms we'll be seeing this week, and then they'll come up again actually quite a lot when we talk about both discrete and continuous models. So this is something that's important for us to know about. So, for example, let's say A was the matrix 4, 2, minus 2, 0. Then I'm going to assert to you that 1 minus 1 is an eigenvector of A. And we can verify that by multiplying A times this vector x. And what we're going to get out is that this is going to be equal to 4 times 1 plus 2 times minus 1, which is 2. Minus 2 times 1 plus 0 times minus 1, which is minus 2, which you should be able to observe is 2 times x. So that is telling us that x is an eigenvector and 2 is its eigenvalue lambda. So is this concept clear to everyone? Right, so if we have an n by n matrix, that can have at most n eigenvectors or eigenvalues. And we'll often use that fact to construct what's called an eigendecomposition. So an eigendecomposition is something that's defined for a non-singular matrix A. And an eigendecomposition is a way of taking A and turning it into a product of three matrices, X, lambda, and X inverse. So X is going to be a matrix of the eigenvectors of A, and lambda is going to be a diagonal matrix. Can anyone remind me what diagonal means? Yeah, so it's 0 everywhere except in the diagonal entries, and on the diagonal it's going to have the eigenvalues. So this is something we'll be using later in analyzing Markov models, among other things. So just be aware this is something you can do. You can decompose a non-singular matrix into a product of three matrices, where one of them is a diagonal matrix of the eigenvalues. Okay, so finding eigenvalues is not necessarily a trivial thing to do. There are good numerical algorithms for doing it. I've never gone through those in this class. It's just one of those things that it's useful to know, but we can't cover everything. But be aware that some of the linear algebra references that are referred to in the text will have algorithms for this. I do like to give you a simple algorithm you can use if you have to do this by hand, so if you're working with a small case, and that is that eigenvalues of A are solutions to the following equation: determinant A minus lambda I equals 0. So in other words, you take A, you take the identity matrix of the same size as A, multiply that by a variable lambda, take A minus lambda I, and then the determinant of that will be a polynomial in lambda, and the solutions of that polynomial equals 0 will be the eigenvalues of A. Now, polynomials you can't necessarily solve beyond small cases either, but at least this gives you a way of finding these in general. And I can show you a simple example of how this would work. So let's say we have the matrix 2, 3, 1, 0, and we want to find the eigenvalues of this. Then what we would say is that we want A minus lambda I. So lambda I is going to be the matrix lambda 0, 0, lambda. So A minus lambda I is 2 minus lambda 3, 1, 0 minus lambda, which is just minus lambda. And if we take the determinant of that, that's going to be 2 minus lambda times minus lambda, minus 3 times 1. And if we multiply through this, as I mentioned, will become a polynomial in lambda. So in particular, this will become lambda squared minus 2 lambda minus 3. And I've asserted that the eigenvalues of the original matrix here are the solutions of this thing equals 0. In this case, it's a quadratic, so we can use the quadratic formula, and we're going to end up getting that, oh, you don't even need it in this case. You'll get lambda plus 1, lambda minus 3 equals 0, or lambda equals minus 1, lambda equals 3. So that will tell us that the eigenvalues of this matrix are minus 1 and 3. The eigenvectors you can actually solve as linear systems if you know the eigenvalues. So in particular, we can say that if we know that there is an eigenvalue of minus 1, then we can say there must be some eigenvector of the form 1 times x. Doesn't matter how you scale an eigenvector, but it's still an eigenvector, so we can just fix one value to 1. And then we can say that 2, 3, 1, 0 times 1x must be equal to minus 1 minus x, and then we can try to solve for x. So we could say, in this case, that we're going to end up with, let's see, 2 plus 3x equals minus 1, so we can get that x is minus 1, and then we would know that the eigenvector associated with this is going to be 1 minus 1. So that would tell us there's an eigenvector 1 minus 1 with associated eigenvalue minus 1. You could do the same thing with the other one. Everyone follow that? Okay, so sometimes this is worth knowing for 2x2 or even 3x3 matrices. Anything beyond that, you'll want to use an algorithm to do it. And if you are using MATLAB, which is something I recommend for some of the problem sets coming up, these are all basic operations. You can just take a matrix and ask it to give you the eigenvalues or eigenvectors or whatever. If not, you can refer to our textbooks or find a library. Basically any modern programming language, there are linear algebra packages you can get for it. And so any questions about any of that? All right, so one last concept I wanted to introduce that's related to eigenvalues and eigenvectors is the concept of singular values. So singular values of A are simply eigenvalues of A transpose A. So take any matrix A, take A transpose times A, that's going to give you a square matrix, find the eigenvalues of that, and those are known as the singular values of A. One of the reasons this is useful is that for any matrix we can get a singular value decomposition. A equals U times sigma times V, where sigma is a diagonal matrix of the singular values. And this doesn't depend on A being non-singular. We can always find this. And singular values end up coming up quite a bit in applications that are important to model inference as well as important to biology and just big data analysis in general. So it's a good term to be familiar with. For example, some of you, if you worked with gene expression data, might be familiar with principal components analysis, or PCA. PCA is basically a technique that is pretty much doing a singular value decomposition. It's more or less the same thing. And one of the reasons we do this is because if you take the singular value decomposition of a matrix, we'll get this U and V. Those don't have a simple explanation like with the eigen decomposition. Very often what we'll find is that you can sort the singular values, and after the first few singular values, they're all pretty close to zero. Not quite zero, but about zero. And that ends up being very useful because you can take all these ones that are zero, just set them to zero, and effectively shrink your matrix and end up with a much more compact system that's almost the same as your original system. There are, of course, degenerate cases where this doesn't work and all the singular values are large, but in general, with real-world data, you often have a lot of correlations among the data, and will end up that the system can be described in terms of just a few singular values and then associated vectors of the matrix V and U that are related to those singular values. So the point of telling you this is simply that it's a common way of simplifying a complex data set. So take a complex data set, do the singular value decomposition, throw out all the small singular values, and then get a dimension-reduced data set. It's a technique that comes up quite a bit, and therefore I just mention it in this context. All right, so those are terms we should be familiar with, so be aware if I refer to singular values or eigenvalues or eigenvectors later, so this is what I'm talking about. But essentially, those are the kinds of key concepts I wanted to mention about linear algebra. So just to reiterate what I said at the beginning of the lecture, this isn't a substitute for a real linear algebra class. It's something any of you working on any kind of modeling or computational science should really take if you haven't already. But hopefully, this gives us at least the concepts and terminology so we're all on the same page for the next few lectures. Are there any remaining questions before we break for today? Okay, then I guess we'll stop a minute.